Okay, so we're going to tie a lot of the things together that we've done so far in Unit 8. We've talked about pH, we've talked about titrations, we've talked about Kas, Kbs, we've talked a little bit about equivalence point and endpoint. So let's tie all these together today. I also thought it'd be a good time to review if we're doing acid-base titrations and you're using sodium hydroxide, even though you think you're measuring out a specific amount of sodium hydroxide making a specific molarity, there are issues with that, and so you have to standardize the sodium hydroxide. And here are our issues. We have carbon dioxide in the atmosphere, nothing we can do about that. And it's going to, a little bit of it is going to dissolve in the water that sodium hydroxide's in, and it's going to make carbonic acid. And then carbonic acid can neutralize some of the sodium hydroxide that we had in there. On top of that, remember that solid sodium hydroxide absorbs water from the atmosphere. So when you think you're weighing out 10 grams of it, 9 point whatever grams actually will be sodium hydroxide, and a little bit of it will be water. So we will have to standardize our sodium hydroxide previous to doing any titrations. So what we think is a 1 molar solution, 0.1 molar solution of sodium hydroxide might end up being a point, I don't know. There's a lot of leeway to that, but maybe that's our molarity after we standardize it. Also, we can review again equivalence point and endpoint. Equivalence point is when typically, if we're doing monoprotic acids and maybe sodium hydroxide, it's when the 2 moles are both equal. But if you're doing diprotic or something that has more than one OH minus, then we'll just call it equivalent. So basically, when you're doing an ICF, a stoichiometry, both of the reactants are limiting reactants. And then endpoint is when the Keller change occurs, because these are typically clear materials, the acid and base, so can't see that the equivalence point has been reached. So we would like to add a pH indicator, and we'll talk a little bit about pH indicators today. So let's talk about pH indicators. And pH indicators are actually themselves weak acids in conjugate bases. So maybe this particular, so we used to call these HAs, and we can still call them HAs, but a lot of people call them HINs. They're weak acids, and maybe this one has a color of blue. And when you have HIN, then you would get, when I say you have more HIN, if you have definitely a 10-to-1 ratio of the HIN compared to the conjugate base, you will have a solution that would look blue. If you have a lot more of the IN minus, the conjugate base, maybe this one's yellow, then you would have that color. So, and these are rules of thumb, but certainly not set in stone that it has to be a 10-to-1 ratio. But it's primarily, if you have primarily one compared to the other, you're going to get that color. Somewhere in between that, when these ratios are somewhere between a 10-to-1 ratio, you're going to get a mix of the blue and a mix of the yellow. And the reason I picked these 2 colors is because you'd actually see this as a separate color. I think today, if we had a solution that had some of the blue and some of the yellow, where not one of those is the primary component, you would actually see it as green. It would look like it's a third color, but really it's just a mixture of blue and yellow. And what we'd like to happen is, let's go back up here to this original. Since this is a weak acid, HIN, it has its own Ka. And what we think about when we did the Henderson-Hasselbalch, let's change those now to IN minus and HIN. If these two items are close to the same amount of each other, then that would give you, dividing those two would give you 1. Log of 1 is 0. So pH would equal pKa when you have an equal amount of HIN and IN minus. So if you know that you want the color change to occur at 8, then you might want to find a pKa or a Ka. pK would be 8. The Ka then would be 1 times 10 to the negative 8th. You're not going to get one. You'd be very lucky to get one exactly where you need it to be. But the closest you can, the better. The closer you can, the better. And you're okay to be a little off, because if you remember, here's our titration curve. And let's exaggerate that a little bit more. Between here and here, the volume of sodium hydroxide changes so little that you actually have a lot of pH here to pick from. I don't have any scale. I don't have a scale on there, but there are a number of pHs that you could pick from that would give you a color change where only 1 or 2 drops would impact that and have that color change occur. Here is a few select indicators, and let's look at a couple of these. So, like methyl violet, for example, at pHs that are extremely low, you get yellow, and it'll stay yellow and yellow, yellow, and then somewhere in that range, it starts to change over into a violet, and it would stay violet, by the way, as long as you keep on going. The one that people typically use in first-year chemistry, actually in second-year chemistry also, is phenolphthalein, because there's not that intermediate color that I was talking about. Like I think I had that example of yellow and blue, and you get that green. It's very difficult to tell when yellow becomes blue because you have that intermediate as green. So people try to steer clear of those when possible, but phenolphthalein goes colorless, so this whole way it's colorless until, I don't know, it is hard to say, but as soon as you can identify any pink in the solution, then you stop. Now if you keep on going, it gets so dark pink that you've went way past the equivalence point, and you kind of have to start that titration over again. So let's erase some of these things here. So if I had a titration where maybe I knew that the equivalence point was at pH 4.74, we had one of those the other day. Which indicator would we want to pick? Would we want to pick phenolphthalein? No, because it changes, I don't know, somewhere in that range. So that wouldn't work. We would want something that changes in the 4.74 range. So let's go close to 5 here. So I think if you used either of these two, this would be appropriate. Remember that, again, your titration curve at the equivalence point has a very, very abrupt vertical portion to it, and you could pick an indicator, any of those ranges there, and it would be fine. When I say those ranges, like here's my pH curve. Now I didn't really put that together very well, but there's a lot of leeway there. So Bromkriesel green or methyl red would be terrific, other than it's difficult to tell when yellow becomes blue, or in methyl red's case, when red becomes yellow, because intermediate between red and yellow is orange. So those are a little more problematic, but as far as theoretical, they're just as good as each other. Okay, we've actually done this question previously, but we just didn't draw the titration curve. So you're going to have to, so in the last section, actually it was 2 sections ago, we took all the math, we got all the math done to get those 4 data points. And today we're just going to, again, I'm just doing this by freehand. On the test, I would have a piece of graph paper in there that you could do this on, or if you had a grapher, you could do this on your grapher if it was a textbook question. But we'll do the best we can here, and I'll kind of refresh your memory to those answers. But if you want to go back and look at the math, that's from 2 sections ago. Okay, so we need a graph paper. We're going to add sodium hydroxide in our burette, drip, 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 and over here we have pH. I guess we should label this, so I'll label this. I don't remember if it was told to us what acid it is, acetic acid, so maybe we better change that and make it acetic acid. Okay, so we have a title, we have labels. Since I don't have, this is freehand, it's not going to be very good here with my increments, so I'm not going to even attempt to put my increments on here. We'll just do the best we can freehand. Let's go back. It was told to us 25 milliliters of 0.1 molar. And we have 0.1 molar of the sodium hydroxide, so therefore we know some points. Now let's actually change this to red. So we know that at some point we'll reach the equivalence point, and that'll be the equivalence point. We know that there will be a halfway point. Of course, there will be a initial point. We're not going to put a little increment on there. And then out here somewhere, it doesn't really matter where this would be, but let's try to make these, this would be about 37. Let's go another one. I don't know, let's say that around 50. And we'll do out there. So there's our points, or at least our x-axis spots. If you remember, when we initially went back here and figured out what's the pH of a 0.1 molar acetic acid solution, we needed a Ka. The Ka was 1.8 times 10 to the negative fifth. And that's always going to be x squared divided by whatever our initial was, in this case 0.1. Solve for x, that's hydronium. Take the pH, take the negative log of that to get pH. And that pH, when we did that, was 2.87. Let's move this a little bit. So let's put 2.87 right there. Okay, again, I don't have any increments on my y-axis, and I'm not going to attempt, well, maybe we will. Let's go back there and whoops, we didn't want to do that. Let's see if I can just erase that. Okay, so let's give this a shot. We'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7. Okay. So we had 2.87. Now those aren't, again, they're not perfect increments, but that's the best we can do there. Okay, so then our second point, the halfway point, if you remember, pH equals the pKa at the halfway point. The reason being is because we produced A minus and we had HA left over, and those two are identical amounts at the halfway point. So if you divide those two numbers, you'll get 1. The log of 1 is 0, so that just wipes all that out. So pH equals pKa. So the Ka is given 1.8 times 10 to the fifth. Well, sort of given. It would be given on the test. We've previously done this one. So you take the negative log of that gives you 4.74. So 1, 2, 3, 4.74. I don't know. Maybe it's around 1, 2, 3, 4. Maybe it's around that spot. And then it was told you halfway point. So it's going to take us 12.5 milliliters to get halfway to 25. So that's going to put us into that spot. So that was 4.74. Okay, so we have two dots so far. The equivalence point, remember that you have a couple things going on here. So we have the weak acid getting neutralized, and it's going to make water, which we don't care about, and A minus, which we really care about. The A minus then impacts water, and it has the ability to produce hydroxide. And so we'll need a Kb value, and you have to take a Ka that we had and turn it into a Kb, and that's going to be 5.6 times 10 to the negative 10th, and x squared up top, and the molarity down below. And remember that when you do this ICF, you will get moles of A minus, but you need to divide it by the total volume. So to refresh your memory, I think we ended up with 2.5 times 10 to the negative third moles of A minus, but we had 25 milliliters plus 25 milliliters, so 0.05 liters is our total volume. So that comes up with 0.05 molar. So that you can solve that to get to hydroxide. Take the negative log for POH, and then 14 minus that to pH. If you want to see that work, it'll be on, again, 2 sections past. But remember that, I'll actually put it up here. The pH at the equivalence point for this must be past 7 because you are making hydroxide. Oops. So I think that came out to be 8.72. So let's go. We have 7, we have 8. 8.72 is about there, and 25 milliliters. I'm doing this freehand here, so it may be a little off, but that would be fine. If you had to do that freehand on a test, obviously there's leeway there, a good bit of leeway. So that was 8.72 for that. And then that last point, somewhere approaching where the beaker or the flask, whatever it has, is primarily just sodium hydroxide. It was a, let's go back here. It was a 0.1 molar sodium hydroxide solution. So if you take the negative log of that, you'll get a pOH of 1. 14 minus that, you'll get a pH of 13. It will never get to 13, but it'll approach 13. So let's go to 13. And let's try to make it that it kind of hugs that, but never quite gets to that, that number 13. And it's very hard for me to tell if I'm closer to that 12 pH or 13 pH, but again, there's a good bit of leeway here as long as you don't have a piece of graph paper or a graphing calculator. But we now need to assemble this, and it would appear that that's almost 4 points that are almost in a straight line. But we don't want that to happen. We need this to be kind of vertical. We need this to approach a more horizontal, and we need this to be somewhat more horizontal than anything else. Remember that at the halfway point, that 4.74 pH at 12.5 milliliters, that's a perfect buffer, so it should be able to resist pH change, meaning that it should be fairly horizontal. Equivalence point, very, very vertical, and then so forth with our last point. So we'll just do the best we can here to get this to happen. Let's go purple here. And again, there's a lot of leeway. Initially, you're not going to, when I say initially, right off the bat of the titration, you're not going to get much in the way of a buffer. So the resistance to pH change won't be that great. But then as the system has more HA and A minus, it becomes a better buffer. And then at some point, the HA starts getting used up more and more and more. So the buffer ability gets less and less and less. And again, it'll approach 13, but it won't ever get to pH 13. And now that I look at that, I'm looking like that's my line goes more to pH 12. That's fine though, that's fine. So we have a very important point initially, a very important point halfway to the equivalence point, another very important point, the actual equivalence point, and then somewhere where it's approaching our limit. What would be our best indicator for this? So we would want an indicator, really actually we would love an indicator somewhere in this range. Do you see that the volume of sodium hydroxide changes very little in anywhere in that vertical column? Our best bet would be 8.72, but we'll do the best we can. And what falls into that range? I guess it would be best to use Creasel red. Okay, so if we go back, we're gonna get a yellow solution. Afterwards, we'll get a red solution, and then in this range here, that's where it's changing over from yellow to red, and we probably will see that in somewhat of an orange. A couple other questions here. This looks to be a free response question. Now let's break these down before we go much further here. Solution X, strong base, strong acid. So keep that in mind, strong acid plus strong base. And it looks like we have the same identical molarities and volumes. So at the end of the day, if you added these together, you should get a pH equaling 7. The second one, sodium bromide, that's just a salt that has no impact on water. And then we have a strong base. So, I'm sorry, strong acid. So we basically just have a strong acid that's being diluted with some extra water. So instead of a 0.1 molar H positive, I guess it's really a 0.05 molar H positive. But that pH is going to be very, very, very low. Lower than 1. I'm sorry. It's going to be a little higher than 1, sorry. And then solution Z has a weak acid and its conjugate base. So that's a buffer. That's a buffer. And its pH is going to be its pKa. We do have a Ka, so that's going to be 4.74. You would just take the log, negative log of 1.8 times 10 to the negative fifth. And we've used acetic acid enough that I think you might remember that that's the value for Ka, for the pKa. Okay, so let's rank these. A says rank them from lowest to highest. I think we said it was going to be solution Y. And then I guess 4.74 is lower than pH 7. And we can visit these answers. I have all the answers on here also. Let's answer a couple other questions here. Does the pH of solution Y increase, decrease, remain the same when water is added? Well, if you add water, all you're doing is diluting that sample. So I think the pH is going to increase because the molarity of H positive is going to go down and down and down as you dilute it. And then solution C, question C. You add sodium hydroxide to the Y and you add to the Z. So let's go back and refresh our memory what those are. The Z is a buffer. So if you add acids or bases to a buffer, it's going to resist that pH change and it's not going to change much. I bet that's what the question says. The pH of solution Y changes more than the solution Z. Explain. So I think it's going to be about a buffer. And we can look at those answers, but I think those match up with what I had already mentioned. And our last question, this ties in a lot of different things. So it's appropriate for what we're doing right now, but also it's about intermolecular forces too. So how is that possible? Okay, so first of all, let's highlight a few things here. If we have HIN, we got yellow. If we have IN minus, we got blue. Let's see here. And it's also told to us, let me write this over here. So the pKa is 5. Each beaker has a layer of colorless oil, okay, on top. In beaker X, the pH of the solution is 3. So maybe that's going to be important. And this one has a pH of 7. A small amount of HIN is placed in both beakers. The mixtures are stirred and the oil and water layers are allowed to separate. What's the predominant form of HIN in the aqueous buffer in beaker Y? Let's see. So let's actually talk about this buffer idea first. Okay, so this one has a pH of 3. So this is for X. pH 3 equals pK, which is 5. So we need this to be a negative number. Why? Because we need this to subtract from 5 to get down to 3. And the only way you're going to get that to happen is for that all to be a negative. And the way you're going to get that to happen is you need that number to be bigger. I don't know if that's how they answer it or not. they don't mathematically answer it that way, but you can use their preferred method, or you can use mine for A there. Either one's fine. Question B. So let's erase some of this stuff here. Okay, beaker X. Okay, so this is about beaker. Well, actually, it's about beaker X and beaker Y. The oil layer is yellow, so let's put that in there. So what's yellow? That's the HIN. So that means the HIN is in the oil yellow, is on the oil layer. With beaker Y, it says the oil layer is colorless. So that means that the HIN has to be there. Okay. Oh, actually, we'll just leave that out for a second. If the HIN in beaker X is in the oil, that means that the water layer has that. And let's talk about why that would be happening. So here's water. And IN minus would be attracted ionic dipole. So that explains why the IN minus is going to be in the water layer. And then why would HIN be in the oil layer? Well, it must be nonpolar, and there'd be an LD, London dispersal force attraction for that to occur. So that at least deals with the that deals with the interparticle forces. But let's see about the acid-base equilibrium. We can kind of use this same idea here. So let's go 3 equals 5 plus log. That's the same thing that I just had in there before. But in the other one, oil layer is colorless. Let's see if they match up with mine there. Let's go down to this part. So they did mention the charged particle. Oh, they did mention ion dipole. I called it ionic dipole. They called it ion dipole. And we talked about the Henderson-Hasselbalch would give you the idea of why you need more of one as opposed to the other, because you need the pH to equal the pK. Well, the pH doesn't equal the pKa. So that means that you need this to either subtract or add so that these two can reconcile. So like one of those was that, so you'd have to have a subtraction there for that to occur. I think that's it for today.